Okay, in this video, we're going to cover section 6.5, and that is on the law of sines. We're going to skip 6.4 because 6.4 is on inverse trig functions and right triangles, and we already introduced the inverse trig functions in chapter 5. The idea was basically, although the functions the trig functions are not injective or one-to-one because they're periodic, they repeat. If you restrict the functions to a certain domain, you will get an injective function, and therefore you can find the inverse on the restricted domain. So it won't have an inverse on all of the whole real line, but it'll have the trig functions will have an inverse on some small interval of the real line. And when we in section 6.4, you revisit those inverse trig functions through the right triangle or the angle approach of trig functions, and you're going to get the same trig functions. That was the whole point of the other video, is that these two approaches to defining the trig functions give you the same functions. So I'm not going to go over it because it's basically the same, although I encourage you to look at it. I think there's, let me see, there's an example you should look at. Let's see. So this is example. So example 7 and 6.4 you should definitely look at. It's not too bad. It's not too hard, but it's something that might come up in the homework, and you should be familiar with how to solve that sort of problem. So yeah, we're going to skip 6.4 and just move on to 6.5, which is the law of sines. Okay, so this is not what I want up. So as I said, this is 6.5. This is the law of sines. And then this section, we're going to learn some methods for solving a triangle, which sounds familiar. Sorry, not familiar, but sounds odd at first. What does it mean to solve a triangle? Well, to solve a triangle means you're given, it's like the most important features of a triangle are it's the lengths of its sides and the angles that are formed by the sides joined to a single vertex. So to solve a triangle means roughly you're given some information about the triangle, maybe some sides or some angles, and you want to solve for the rest of you want to solve for the other sides and angles. You want to determine what their measures are. So that's all that means. So we have 4 cases, really, 4 different types of triangles we can solve. And I'll bring up this diagram. So, and these exhaust all the cases right here. So you have angle, side angle, or side angle, angle. And that is, you have that, you're given a length of one side, and then you're given the length, or you're given the measure of 2 angles, right here and right here. And then you're given the length of the side connecting those angles. So what you need to determine in that case is this other angle right here, and then these 2 dotted lines. These are the other sides that are unknown. So that's one case. The other case is side angle. That means that you're given 2 sides joined by a vertex here, and then the angle of measure of one side. So the other thing you need to determine is this dotted line here, the length of this, and then these 2 other angles. The other case is side angle side, That's the case where you have these, you're given these two sides, their measures, the lengths, and then you're given this angle and you need to determine this angle, and this other side. And then finally, there's just side. You're just given the sides, the measures of the sides. And what we're going to use is these trig functions that we've defined. And we're also going to use some other facts about triangles that you've learned probably in, I don't know, high school or whatever, or maybe earlier than that. And one of those facts being that the sum of the angles adds up to 180 degrees. So that would be a helpful fact. Now you might say, like, this really actually exhausts all the cases. What about the case where you're given just angles? So there's several cases. Like, you could be given two sides and an angle, two angles and a side, and then there's just different ways of having those sides or those angles. Or you could be in this last case where you just have all sides. That's all you know. What about just knowing angle? Why don't we consider that case? Why is that not part of the cases? Well, the reason is that that case is not you can't determine it. It's not unique. That is like an indeterminate case. You can't determine the triangle from that. So suppose I give you this triangle, and all I know are this angle, theta 1, call it theta 2, theta 3. And you might ask yourself, okay, from this information, can I determine? So the question is, can I uniquely determine the lengths of the sides? And the answer is no, because there are many triangles compatible with this. Namely, all I have to do is just blow it up. I don't know if I can do that. Blow it up in the sense just make it bigger. So let me see if I can do that. I don't know why this is not working. Okay. So if I just extend the lengths of them, so this is supposed to look roughly the same. The idea, though, is that the amount I've lengthened all the sides by the same factor, the same amount. But what's still the case is that this, for example, this side right here, to rotate this side onto this side right here, I still have to rotate the same amount, namely theta 1. And the same thing for these other angles. All these other angles will be the same. But the lengths of the sides are not the same as the lengths of the sides of this first triangle. So just given those three angles, it's not enough to determine the whole triangle. There's a whole infinity of triangles that are compatible with those angles. In fact, these form like what we might call an equivalence class. They're equivalent in a sense. These are actually called similar triangles. This is, so you can think about like all these. Yeah, these are all these. So yeah, the angles in this case don't uniquely determine the triangle. There's an infinitude of triangles compatible with these angles, and these triangles form what's called an equivalence class. So this case we will not consider. We will consider the other cases. So let's look at let's think about those cases again. It's going to turn out that so there's 4 cases, and it's going to turn out that only the methods we're going to learn in this section are only applicable to 2 of the cases. In the next section, 6.6, we'll learn about how to cover the other 2 cases, the last 2. So case 1 is one that we're going to deal with in this section, and that's when you're given one side and 2 angles. So that's what we call the angle side angle, or the side angle angle case. And then the other case is when you're given 2 sides and the angle opposite one of those sides. So this is called the side-side angle case. So let's introduce the law signs, which will help us solve these or deal with these or handle these cases. So the law, here's just the statement of the law signs. So law of signs. So in a triangle ABC, we have the following equations hold. We have a system of equations. So 3 equations. Well, no, not actually more than 3 equations. So you have first can be second, but 1, 2. Oh, no, actually 3 equations. Okay. Sorry. So we have a system of 3 equations. And it relates the angles and the sides in the following way. So we'll just draw some triangle. It's supposed to represent any triangle. And these 3 equations hold for any triangle. It does not matter the nature. It does not matter the nature of the triangle. So we have these 3 angles, A, B, and C. And then we have the sides. Now notice the labeling. You have to be careful about how you label the sides. In fact, I did not label it correctly myself. So we have to be careful about how you label the sides of the triangle. Otherwise, the equation will not be valid. So the idea is that you have this angle here, A, angle B, and C. The side across from A, angle A, is side A. The side across from angle B is side B, or side of length B. And then the side across or opposite to angle C is the side with length C. And if you have a triangle set up in this way and labeled in this way, then these system of equations hold right here. And you can use them to solve the triangle, which, as I said, means solving for the rest of the essential information about the triangle. The essential information being the lengths of the sides and the angles. So let's look at an example. This is example 2 in chapter 6.5. So the triangle looks something like that. So we have A, and it is a 20-degree angle. Then we have B. B is unknown. So this is, as I said, this is the side angle side. Or side angle angle, or angle side angle. I don't like that, so I'm just going to say angle side angle. So what we're given is angle A, angle C, and angle C is 25 degrees. And then we're given the length of side, or we're given the length of the side opposite to C, which is 80.4. So this is A, we don't know what that is, and this is B, and we don't know what that is either. So we want to solve for A, B, and then angle B. Well, we can actually right off the bat determine B. So angle B, so recall the sum of the angles is 80 degrees, it equals 180 degrees. So we have angle A plus angle B plus angle C is 180 degrees. It's 180 degrees. So we can substitute things in. So A is a 20-degree angle. C is a 25-degree angle. And then that, if we solve for B, we get the following. We get 180 degrees minus 20 degrees and minus 25 degrees. And if you do that, you get 135 degrees. So that gives us the one piece that of information that we're looking for. Now we just need to find angle B and angles, or no, sorry, not angle, but side A and side B. So to do that, now we need the law of sines. So recall that the law of sines, one equation in the law of sines is that sine of A over A, notice how the correspondence, it's sine of A over A. So the A's, you always match up the A's, and then sine of C over C, match up the C's. So we know sine of A, we know A, we know sine of C, we just need to solve for C length. So if you do that, you're gonna get, I'm sorry, we know C. What we want to solve for is A. So if you do that, you get, if you do the arithmetic or you do the algebra, you get A is equal to C times sine of A over sine of C. And then substituting in, we get 80.4 times sine of 20 divided by sine of 25. And to get an approximate value for this, you need a calculator. So that's approximately 65.1. So A is approximately 65.1. So this side right here is approximately 65.1. And now we just need to solve for B. So again, we use a similar equation. Sine of B over B, so the B's go together. It's a ratio of those B's in some sense. And then you get sine of C over C. We're looking for B, so we're going to solve for B. When you do that, you get C times sine of B over sine of C. And if you plug in all the, I'll just plug the numbers in. It won't kill me to plug the numbers in. If you plug the numbers in, you get 80.4 times sine of 135 degrees divided by sine of 25 degrees. And if you do that, you get, if you plug that into calculator, you get that this fraction right here, and hence B is approximately 134.5. And that solves the triangle. So to solve this triangle, we first had to use the fact that the sum of the angles is equal to 180 degrees. And then that enabled us to calculate B. And then once we did that, we used the law of sines. We used the law of sines to first find the length of A, which was approximately 65.1. And then we used the law of sines again to calculate the length, B, which we determined was approximately 134.5. So in this, so this was actually, this is the correct label. I guess there are two cases here. So let me just keep these distinct. This is not side, angle, side. This is, let's just use the note, let's just use the names they use. So this is side, angle, angle, as they did, as I wrote initially. So now we're going to continue this, studying the case where you're given one side and two angles. But in this case, this like a sub case is the so-called ambiguous case. So the reason it's ambiguous is because that it's not that the angle is or the triangle is not uniquely determined. It's just from face value, it seems like there could be multiple triangles, but you have to use further analysis to rule out some possible triangles. Like for example, well, in this contrast, the case of angle, 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 that there's no way of ruling out. There's no way of knowing, like if a person gave you a triangle, they said, here's a triangle, and they said, these are the three angles. There's no way for you to determine what the triangle that they gave you, because as we saw, that there's an infinite number of triangles that agree or correspond to having those three angles. So in that case, the angle, angle, angle case, it's more than ambiguous, it's just indeterminate. But in this case, we have ambiguity because we have to do some further analysis to rule out possible, or what seem like possible triangles, but they'll end up not being possible. So, and they'll come about when you determine, so this is the side, sorry, this is the side case. And so the ambiguity will come about in determining the angle, other angle. It will, when you solve for the angle, you could possibly have two values, and you have to just basically rule out why one of them is not possible. So let me just show you this picture to illustrate that. So this is the ambiguous case. So let's see what they say. So as they say, in the case one, which we've already looked at, we're now going to do case two. So in case one, you can uniquely determine the triangle, which is angle, side, angle, or side, angle, angle. But in case two, we don't have that. The case two being when you have two sides and an angle. So so if you look at this right here, yeah, like let's just focus on C and D, or even B. So that you're given the length of B and A, you're given angle A, but you need to say determine C and D. But notice with this setup, there you could have multiple triangles, not an infinite number of triangles, but just a few triangles. In this case, there's like 3 triangles that are consistent with those information. So you need more information perhaps to rule out the other cases, or maybe you just have to say it's not you. It's the triangle is unique up to these like 2 different types. So like, or 3 different types in this case. So look at, if you look at this side length A, you can rotate it at different angles. So this will give you in B, C, and D, or so these cases, case B, case C, should use numbers. So case 2, case 3, and case 4, the angle C is different in each case, but the side lengths are the same and angle A is the same. So the only side length is not the same as C. That also changes because that will depend upon the angle you rotate C out, or the angle that C is. So we're going to learn how to deal with this ambiguous case now. So this is going to be side. This is example 3. This is side angle. So we're asked to solve a triangle called A, B, and C. And then we're told that angle A is a 45-degree angle. We're given the length of A, and that's 7 times root 2. And then we're given B. So we're given 2 sides and an angle. So let's draw the setup. So from the start, we don't know whether this is the only triangle. I'm going to just draw a single triangle, but it's possible to draw another triangle or construct a triangle that's consistent with the data we gave. But let's just draw some picture so we have a reference. So we know how to use, so we can actually apply the law of sines. So we're given A, we're not given C, and we're not given B. So we need to determine these. And in this case, we can't use the fact that the sum of the angles is equal to 180 degrees, because in order to use that, we really need to know 2 angles, and that will help us determine the third. So side B is equal to 7. This is the unknown side. And then side A is 7 root 2. So we can't use that nifty fact about the sum of the triangles being 180 degrees, but we can use the law of sines to solve for B. So we're going to use the fact that sine A over A is equal to sine B over B. So if you do that, you get sine B is equal to B times sine A over A. And then that's equal to this if you substitute these numbers in. And if you remember, sine of 45 degrees is root 2 over 2. Actually, let me just write it in. So obviously these 7s cancel out. You have this root 2. Now sine 45 degrees is root 2 over 2, and then this will cancel to give you 1/2. So the angle has to be some number between 0 and 180 degrees, because we're talking about an angle within a triangle. So we need to ask ourselves what number, what must be, or let me just, because we have a bunch of equations and it might not be clear what the question is. So this calculation right here tells us that sine of B is equal to 1/2. Now sine of B, so B has to be some angle between 0 and 180 degrees. Or if you're thinking of radians, which it really should be, I don't know why they're not doing this in terms of radians. If you're thinking in terms of radians, that's 0 and pi. So let me I'll put this in quotation marks because this isn't like strictly rigorous maybe. If you're thinking in terms of radians, it's 0 and pi. So we need an angle between 0 and 180 degrees such that sine of that angle is 1/2. Well, it turns out there are 2 numbers actually. If you get your unit circle out, or if you're however you think about angles, we have these 2 approaches to thinking about angles at this point. You can find that B could be either 30 degrees or 150 degrees. So at this point, it seems like there could be 2 triangles. One triangle where that angle B is 30 degrees, or one triangle where that angle B is equal to 150 degrees. But now we're going to use that nifty fact about the sum of 3 angles being 180 degrees. We know that at least we know that this must be true at least, right? Is less than 180 degrees, right? It has to be less than 180 degrees because the sum of the three angles has to be equal to 180 degrees. But what is the sum of, so we want to actually rule out one of these angles. This is basically like a proof by contradiction. So I'm going to write this out by way of contradiction. This is pretty formal at this point. We've been pretty formal. So by way of contradiction, suppose the angle of that angle B is equal to 150 degrees. Oops. Well, does that conflict with this fact? If we suppose that B is equal to 150 degrees, is it compatible with this fact? Well, let's compute the sum of these two angles. Well, we know angle A is 45 degrees, and we know we're imagining for a moment, for the sake of argument, we're supposing B is 150 degrees. If we add these two, what do we get? We get 195. And that is not less than 180 degrees. So this implies that this is impossible. So this is impossible. Now, angle B must be either 30 or 150 degrees. It cannot be anything else. It has to be one of the two. Since 150 degrees is impossible, it follows logically that angle B must be equal to 30 degrees. So this is like a proof technique that's very common in mathematics as you go further along. This is called a proof by contradiction, where you're given a couple possibilities, and you know only one of them can be the case, or maybe two. In this case, we only have two possibilities, and we're ruling out one of them. But so you're given a multitude of possibilities, but you want to rule some of them out. So you do that by contradiction. You say, suppose this is the case, and then you obtain a contradiction. The contradiction we obtained in our case was that this sum was equal to 195, which is greater than 180 degrees. So that it leads to, this is like they say reductio ad absurdum. This is like a proof method. This is impossible. This cannot be the case. So since the only other possibility is that B is equal to 30 degrees, B must in fact be 30 degrees. So this is like a really subtle logical point that trips up some people when they're first learning proofs. So being able to see this at early stages, very beneficial. So this is a very, very common proof method. It's called proof by contradiction. So with this, we can actually determine the rest of the information. I won't go through the rest of it, but I'll just kind of, I won't write it down, but I'll just kind of run through it verbally. So we have two angles now. So we can use that fact that the sum of the three angles equals 180 degrees. And we can use that fact to solve for the other angle. And if you do that, you get that C is equal to 105 degrees. And then so now we have all three angles. And now we'll just use the law of sines to get that last side. And I'll just write down the equation you need. I won't go through the steps. So the equation you need to do that is, for example, this. You could actually use, so we want to solve for a C. And you could use this ratio, or you could use sine A over A. Either one is fine. But you can do that, and you can solve for C, and if you do that, you get that C is 13.5. But you should definitely go through the algebra and arithmetic to figure out why that's the case. So, and this is the case of ambiguity. It seemed like we could have one or maybe two triangles, but in fact, we could only have one triangle. Because if you imagine that B was equal to, was it 150 degrees, you got this absurd, you obtain this contradiction, this absurdity. So let's see. We'll just go through one more example and then we'll call it a day. So this is, in this example, you're not going to be able to rule out, one of the possibilities. This is a case where both triangles are possible. So the setup is, I'm just going to pull the book open because there's a lot of drawing, and writing with this tablet can be annoying. So we'll just run through this example quickly together in the book. So the triangle you're given is ABC. Angle A is 43.1 degrees. Side A is 186.2 and side B is 248.6. We're still in the side angle case. So we already dealt with the one case that was angle side angle or side angle angle. This second case is just side angle. And in this case, we can have multiple possibilities. There's not one unique triangle. There's not an infinity of triangles consistent with the data that you're given, as in the case of angle, 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 but there's a couple possibilities. So from this, they say you can draw two possible triangles, and notice that it seems like just from the drawing that yes, there are two triangles that you can actually draw. So our intuition should tell us that there's probably going to be two triangles, and we probably can't rule out the one or the other. They're both going to be possible. So if you draw that, you get these two triangles kind of superimposed on each other in a sense. So you can solve for. So yeah, what the difference is going to be in the triangles is going to be this side length C. So we have this right here, and with this short segment, or have this whole long segment. And so you have these two angles that you could possibly get. So if you do that, so you want to solve for B. So B is the unknown angle that has two possible values. So if you solve for that, you get this number here, 0.91225. And as they pose that same question, are there two possible angles between 0 and 180 degrees such that this equation holds? And in fact, yes. If you use the calculator, you get these. You get one value is equal to approximately 65.8, or the other one is 114.2. So you have these two triangles, and you go through the same procedure as we have been going through. You use that fact about some of the three angles being 180 degrees. So you have these two subcases. You have triangle A1, B1, C1. So that's this big triangle. And you go through the procedure of solving for the other angles. This will give you two angles right here, right? C has two possible values because B has two possible values. And you just go through the same arithmetic. I won't go through it. You can go through it if you feel like you need to. And that will give you one possible triangle with this possible angle and this possible length for C, or the C1. And then there's the other triangle, this slimmer triangle right here. This will give you a possible angle of that and a possible side of that. So this is the case that you have two possibilities that are actual possibilities. Considering one possibility doesn't lead to a contradiction. These are two triangles that are consistent with the given data. There's this other example. I'm not going to worry about it a whole lot. I'll just say it very briefly. I don't think I'll give you any homework on it, but this is the case where you have no solutions. There's no triangle ABC which has this angle and these side lengths. It's impossible. And why is that impossible? Well, this is another proof by contradiction. The idea is you say, okay, suppose there is a triangle. Obviously, you can't draw it. It's physically impossible to draw this triangle because it's going to turn out to be to lead some sort of contradiction. And this is where proof by contradictions can be tricky because you can't. They can. How do you visualize a contradiction, right? Like for instance, how do you visualize a round square? You can't really. It's impossible. There's no such object that is round, both round and square. It's an absurdity. So you can't really visualize contradictions. So that's what makes these proofs sort of tricky. So you got to proceed a little bit more abstractly and just push some numbers and you calculate some things. But the idea is, as we did above, proof by contradiction. Suppose there is some triangle, for the sake of argument, with a length or with angle 42, side length 70 and 122. You can try to draw it, but this is just not going to be a representation of it. It's impossible. We're gonna, because we lead to this contradiction right here. I'll explain why this line is a contradiction. You can't really draw it, but you can attempt it just to be able to know how to apply the law of sines. So we're gonna suppose there's a triangle, and then we're gonna try solving for it. So we're gonna solve for angle B. So we're gonna use this equation right here, sine A over A, sine B over B, and solve for sine B. If you do that and you calculate this, that you find that sine B is approximately 1.17. Now, why is that impossible? Maybe take a second to think about that. Why is that impossible? Maybe pause it. I don't know if you need to think about it. Pause the video for a second to think about why is that impossible. So if you paused it and you thought about it, the reason why it's impossible is that the sine function, remember, is the absolute value of sine is less than or equal to 1. So remember, the graph of the function is bounded between the lines 1 and -1. So the graph never goes over the line 1. And so therefore, the sine function never achieves values, or its output is never bigger than 1. So this line right here is a contradiction. This is impossible. So therefore, so as I said, since the sine of an angle is never greater than 1, we conclude that no triangle satisfies the conditions in the given problem. So there is no such triangle that has this angle and these side lengths. It's impossible. And this is the contradiction. This will show you why there is no such triangle. So I guess I went on longer than I thought with that example, but it's good because it illustrates this proof by contradiction again, which, as I said, is a very useful technique when you go into mathematics, more advanced mathematics, and you're proving theorems and such. So that's the end of this section, 6.5. Next video will be 6.6, where we learn how to solve these two other cases. Let me go back. So case 3 and 4, where you're given 2 sides and an included angle, or just 3 sides.